Unit conversions is one of those skills that's easy to learn but easy to get lazy with. The problem I see a lot of students have is they don't keep track of their units as they're solving a problem, so they have a final number at the end as a solution, but because they didn't keep track of the units, their final solution units aren't correct, or they might have lost the term but don't recognize it. Now, if they follow the units, you would see that your units don't match what the solution should be, and that's an easy way to check. In the real world, there are real world consequences to bad unit conversions, right? In the best case scenario, poor unit conversions might mean that your assembly doesn't fit together because you converted the length scales incorrectly. There's a lot of examples where there are catastrophes because unit conversions were done incorrectly. Good examples are how much fuel a plane needs, and because of unit conversion, they didn't give enough fuel for the plane, so now it has to land early. So there's a lot of things like that something as simple as unit conversions, we want to make sure we understand the fundamentals of really well, and we're consistent and we're diligent on keeping track of units as we solve problems. So I'm going to show you a few examples and principles that we follow when we do unit conversion. One type of unit conversion is between unit types, English and SI units. In the United States, we talk about temperature units in Fahrenheit. And in almost any other country, we talk about temperature in terms of Celsius. In a classroom and engineering setting, sometimes it's convenient and necessary to talk about temperature with absolute temperature reference. In this case, having some absolute zero. So that would be in Kelvin or Rankine. Now, how do we convert between these different sets of units? Well, we need a few equations to relate them. So a lot of you are probably familiar with how to convert between Fahrenheit and Celsius. So these equations mean if I want to solve for the equivalent Fahrenheit, I would use this equation, plug in the Celsius form, and I would get it. This equation would tell you what the Celsius temperature would be in terms of Fahrenheit. You plug in the Fahrenheit component here. And in terms of the reference Kelvin to Celsius, it's just an offset, right? An offset of 273.15. And between Fahrenheit and Rankine, it's just an offset of 459.67. So what do I mean by offset? It's just, as you can see here, adding or subtracting a value. There is no proportionality factor as there is here when you're converting between Fahrenheit and Celsius. There's this 9/5 or this 5/9 conversion factor. All right, so let's take a look at a couple temperatures and convert between these. All it is really is recognizing these relationships and plugging in values. So we have a few reference temperatures that are convenient to use. One is absolute zero. And so let's assume that we all know that at 0 Kelvin, we have absolute zero, right? This is why these are known as absolute temperatures. If I want to convert between Kelvin and Celsius, I'll go over here to my Celsius and it says plug in Kelvin, the Kelvin value, and subtract 273.15 from it, right? So the Kelvin value is 0. So I have negative 273.15 degrees Celsius is absolute zero. If I want to convert between Celsius now and Fahrenheit, I take that temperature in Celsius and I plug into this equation here. We get 9/5 times negative 273.15 degrees Celsius plus 32. And I get negative 459.67 degrees Fahrenheit. And it's not a coincidence that this value is the exact same as this value. Because now when I want to convert between Fahrenheit and Rankine, I plug in negative 459.67, add 459.67, you get 0. So at absolute 0, you have 0 degrees Rankine and 0 Kelvin. And then in Celsius, it's negative 273, and in Fahrenheit, it's negative 459. All right, what are two other good reference points? Well, the temperature of water at different phases is an important one. So 0 degrees Celsius, we have freezing water, right? So we can convert between these three forms as well, right? So in Kelvin, we just add 273.15. So 273.15 Kelvin is freezing water. I plug in 0 degrees to convert to my Fahrenheit. I get 32 degrees Fahrenheit is freezing water as well. Now I want to convert to Rankine. I plug in 32 degrees Fahrenheit, add 459.67, that offset. Now I get 491.67 degrees Rankine. So you have freezing water, you have absolute zero, you also have 100 degrees Celsius. What's 100 degrees Celsius? That's boiling water. So see if you can do the conversion on your own. And now I'll give you the solution to it. All right, did you get this? 100 degrees Celsius, you want to convert to Kelvin, you add 273.15, you get 373.15. You want to convert it into Fahrenheit, you plug it into this equation, 9/5 times 100 degrees plus 32, you get 212 Fahrenheit. And if you want to convert Fahrenheit to Rankine, you add 459.67, right? So pretty straightforward, you just plug it into a conversion equation. Now there's a different kind of conversion between English and SI units that we'll look at for length scales. Let's take a look at that one now. So let's say we're looking at inches, feet, centimeters, and meters. Now there is a whole set of other length scales, but what I want to show you is how we convert from one to the other, knowing the relationship between one and the other, or one and another one that we know the reference relationship. So let's say the only relationships we know are that in 1 foot you have 12 inches, in 1 meter you have 100 centimeters, and in 1 inch you have 2.54 centimeters, right? Typically, if you memorize this, you can make the conversions that you need for the most part. So let's take a look at a couple examples. So how do I convert 6 inches into feet? Right? So I know the relationship between inches and feet. So I can multiply by either 12 inches over 1 foot or 1 foot over 12 inches. Because 12 inches over 1 foot is equal to 1. 1 foot over 12 inches is also equal to 1. So the way to figure out which form you want to multiply is I want to convert inches into feet. So the ratio I want to multiply, I want whatever unit is up here, I want that to be in the denominator of the conversion. So I'm going to want 1 foot over 12 inches, right? Because this term in red here is equal to 1, since 1 foot is equal to 12 inches. So the units inches and inches here cancel out, so we're left with a foot. So 6 over 12 is 1/2. Okay, it's as simple as that. How about when we square things? So if a unit is squared, the conversion also needs to be squared. If this unit is cubed, the unit's conversion also needs to be cubed. That's a common mistake that when they convert from one to the other, that they forget the square component of it. Okay, so 4 square feet, so that's 4 feet unit squared. I want to convert that into squared meters. So feet to meters, I don't have a direct conversion, but I have feet to inches, then I have inches to centimeters, and then I have centimeters to meters. So I have a path to get there. So that's all you need to look at when you're doing these conversions, is that path. Now we would also need to include the square component. So what would this look like? So from foot to inches, I have the 12 inch per 1 foot conversion. Since this is feet squared, I want to drop this out. I need a feet squared down here, so I could square this whole system. And now we'll have inches squared. So inches to centimeters I can convert. 2.54 centimeters is 1 inch. I would need to square this whole system, this whole term. From centimeter squared now to meter squared, I would need 1 meter per 100 centimeters, quantity squared. Right? So if you multiply these all out, you get 0.3716 meters squared. So take a look at these 3 example problems. Press pause. Try to do conversion in the same way. How many inches are at 7 meters? how many square meters are in 25 squared centimeters, and how many inches are in 2 meters. All right, press pause, and then when you have solved them, come back. Okay, hopefully you solved them or you had a chance to try it. Here's the solutions. From meters to inches, I go from meters to centimeters and then centimeters to inches. That's what's shown here. And just recognize when a unit's in the numerator, you want to put the conversion of that same unit in the denominator to cancel it out. Okay, 25 squared centimeters, so I need 1 meter per 100 centimeters quantity squared for the conversion. And then meters to inches, first I convert meters into centimeters, and then I convert centimeters into inches. Okay, so hopefully this makes sense. The main points are where the unit should be, whether it should be in the numerator or denominator, and then how to handle squared units if we're starting with squared units like feet squared, like we are shown here. All right, so next I want to show you when we have multiple units combined to create a larger unit. How do we make those conversions? Now, units are not just standalone. We can measure the mass of something in kilograms. We can measure the length in meters. But there are certain properties that are a combination of these fundamental units. So for example, the unit for force is oftentimes in SI unit. I'm putting all these in SI units. In newtons. And 1 newton is a kilogram meter per second squared. So kilogram term multiplied by a meter term, length scale term, divided by a second squared, or a time term. This is your acceleration component. This is your mass component. Now, force can come in a lot of different different ways. So we can combine units in a lot of different ways and get some form of mass, length over time squared. And so all of those will have units in newtons. How do you combine those terms correctly to form the correct unit of force? That's important. Energy is that force unit, newtons, times meters, right? This gives us a joule. Pressure in pascals is the force term over an area, so Newton per meter squared. All right, so we're going to take a look at a couple examples that gives us these three full, more complex unit terms. We have some more fundamental terms that we'll use to build them up, like mass, which we'll use M. When we use square brackets sometimes around variables, we use that to represent the units of these. So the unit of mass is in kilograms, unit of density is in kilogram per meter cubed, units of gravity is in acceleration units, meters per second squared, units of Hooke's constant, K is in Newton per meter, units for distance, h, like a height term, or displacement, x term, is in meters. So let's take a look at a couple examples for different kinds of forces, pressure, and energies. So force, mass times gravity, is a weight. That's an example of a force. Pressure, density, rho, times gravity, h, times height. This is a hydrostatic pressure. This talks about when you go deep in underwater or you climb somewhere high, how the pressure changes. That's what this pressure is representing. Then you have the kinetic energy of a spring, right? Because we're looking at this as a spring constant, and then we're looking at x as the displacement from the equilibrium point. So let's take a look at examples using these three complex variables. So let's say I have a mass of 10 kilograms and the gravity is 9.81 meters per second squared. Now I want to determine the force based on this equation, right? Which is essentially the weight of this mass here. So I'll multiply 10 kilograms by 9.81 meters per second squared. Again, 98.1 kilogram meter per second squared. And I can go over here and I say, all right, kilogram per meter per second squared is 1 Newton. So I can do a direct swap. And this will be 98.1 Newtons, right? It doesn't always fall out so cleanly. Let's take a look at our next example. We have density, 1,000 kilograms per meter cubed, like water. Gravity, 9.81 meters per second squared. And the height displacement of 2 meters. And I want to determine what the pressure is. So we go over, we can use this equation, but we want to make sure that the final units are going to be in some form of Newton per meter squared, so we can convert it to pascals. So I'll multiply density, gravity, and height. Density, gravity, and height. Again, 19,620, what units do I have? I have kilograms, meters per second squared. I like to isolate that because I know that's going to give me a Newton. And then I have a meter per meter cubed. So this one of the meters terms cancels out. I get 1 over meter squared, which is my area term. So that kilogram meter per second squared divided by meter squared is my pascal. So I get 19,620 pascals. All right, finally, we have our Hooke's constant, 10 newtons per meter. That just talks about the stiffness of the spring. And let's say that we're looking at displacement of 2 centimeters, and I want to figure out the kinetic energy. So I got 1/2 from this equation times K, 10 newtons per meter, times x squared, 2 centimeters squared. Because it's centimeters squared, and I'd like to keep things in meters, I would need to convert centimeters to meters. I get 1 meter over 100 centimeters, quantity squared. Quantity squared because the centimeter term will be squared. So I get 1/2 times 10 times 2 times 2 divided by 100. We get 0.002 Newton meters. Newton from here. And then we have 1 left over. So this will give us a meter squared. One of them will cancel with this one. The other one will multiply by the meter. Newton meter is a joule. So our final answer is 0.002 joules. So you can see the different ways that we can do unit conversion. The main thing is when you start your problem, keep your units all there. And if you're not sure exactly how to convert it for systems like this to build up, keep everything in your base units. Your base units are in like kilograms, in seconds, in meters, right? These are your base units. You can build a lot of different things from it. Recognizing what general forms you get, right? Like newtons is a general one, joules is a general one. The joule per second is a watt, that's a general one. Pascals is a general one. So all of these tools will help you so you keep track of your units throughout solving a problem. So by the time you finish solving a problem, if your units don't match what you're solving for, most likely you left out a term. So it's a good way to check your work.